Good. So welcome back, everyone. So we learned now how we can use these so-called homogeneous coordinates to do a translation by just putting a line of zeros and a 1 in the last row of our matrix by just adding another dimension to it. And of course the column then indicates the translation value, the values that influence how we do the translation. And for vectors we add a 0, and for locations we add a 1, and then we can do just simple normal matrix multiplication to achieve a translation, which is normally not possible with matrix multiplication because it's not a linear transformation. Translation is not a linear transformation, matrix multiplication is. And but if we extend it by this dimension, then it comes to changes to shearing, so we can do this transformation. And the nice thing is, if we do this with these homogeneous coordinates, the zeros and the ones, both in the matrices and the vectors, it fits into this other matrix multiplication scheme. So we just have to switch to it when we do the transformations, and then we can apply any transformation that we had so far. So the translations and the linear transformations and the translations, which is why these kind of operations we call affine transformations. So affine transformations are linear transformations and translation. So let's use this now to solve a more complicated case to figure out how we can do a more complex transformation. So for example, we have the yellow square here, and we want to reflect this on the blue line, which is the line y equals minus x plus 5. And we know how to do a reflection on a line that goes through the origin, and we know how to do translation now. So the obvious way to solve this is to do a translation to translate everything to the origin, then do the reflection, and then translate everything back. So to do this, first we need a translation. We need to translate y equals x minus x plus 5 to y equals minus x. So we have to put up a translation matrix with two values xt and yt. And we see here from the image, of course, we want to move the blue line to 0 to go through the origin, but not change its direction. We just have to move every point in about 5 in y direction and nothing in x direction. So these two values xt and yt are 0 and 5 respectively. So I already put the matrices here easily to do the matrix calculation. So our first matrix that we apply is this one. Then we want to do the reflection, and we know from the 2D from before, reflection on y minus x is no, we had a different reflection case, but this is pretty similar, that if we apply this, then it basically changes the x and y value and also changes the sign of it. So this is a reflection matrix for along this line. So we just have to, and that's what we have to do. We don't have to do any translation, but we, of course, when we want to integrate it in this whole scheme, we have to add the homogeneous coordinates. And if we look at this, we obviously see if we multiply this with a vector x, y, 1, it will not change the vector. It will be for x and y the same results as if we apply x and y to this two-dimensional matrix. And then, of course, we have to translate everything back. And since the original translation was from just moving it along the y-axis by 5, the backwards transformation is, of course, just moving it by 5 up. So instead of why did no one correct me when I wrote 5 here instead of minus 5? So minus 5, of course, we move it down, and now we move it up. So we have here 0, and here we have 5. Looks like you're also not that fit today. Good. So now we have all the three matrices that we use. We can apply them after each other, but we can also multiply them, because we saw we can combine matrices to create a more to have just one that does then this whole transformation in one step. So if we do this, if we multiply this, so the first one we get 0, minus 1, minus 1, 0, 0, 0, 1. That should not change, and it doesn't, fortunately, because these are the homogeneous coordinates. And here we have 5, 0. And if we multiply that with the last matrix, we get 0, minus 1, minus 1, 0. And here we get 5, 5. And again, here we get 0, 0, 1. And it would be bad, because it would be a calculation error if we didn't, because these are the homogeneous coordinates, and we've chosen them, we have defined them in a way that they will always stay like this in the last line. Good. So this is our matrix now, and if we apply this, let's see if I made it correct. Yeah, it's correct. If we apply this, then we have the the reflection and this line. In one step, we can make this more complex by operation by splitting it in simpler operations and then combining the matrices for these simpler operations. Now, the same question arises, of course, compared to related to what we had before. When we have such a matrix, applying it is pretty easy, but if we have a complex operation, and in this case, I just split it into the simpler simpler operations and then calculated the matrix, but is there also a way to directly find this matrix? Now, if we look at what this matrix does, so these here are of course the homogeneous coordinates. They also always have to be 0, 0, 1. These are just added so we can do the math, but they don't have a geometric meaning. The geometric meaning is of course shifting it in this one plane z equals 1, but other than that we're not interested in that. And if you look at these here, these are exactly the images of the base vector under the linear transformation. So this is exactly this reflection here, which is again the images of the base vectors under this linear transformation. So once we have moved it and then do the linear transformation, these are exactly the vectors that we get. So these are exactly the columns in this matrix here. So the interesting question is here now, how do we get these two values here? What do they represent? And if we look at the image, we see that the point 5, 5 is here. 5, 5. That is exactly the image of the origin under the affine transformation. So this is the affine transformation, and then I create the image of it. And these are exactly the two values we need here. So I will not prove this, so just have to believe me, but this is an easy way to find a complex transformation matrix, not by splitting it down into the simpler operations, but by just looking at it and saying, okay, it's a combination of a translation and a linear transformation. Then this left block here indicates me the images of the base vectors. Here it's written the images of the base vector under the linear transformation. And these values here, so let's make it like that, A and B. These here are the images of the origin under the affine transformation. And here, of course, we have C, the homogeneous coordinates. Good. All right, and there will be more examples like this in the exercises where you have then a chance to practice it. Sorry. Good. So we see now we can do very complex transformations, but we're still in 2D. So let's look at the 3D case, because of course that's what we're interested in graphics. But as I said, it's just a straightforward generalization of the 2D case, but it's of course easier to explain, especially the homogeneous coordinates, because when we do it in 3D we have to move to 4D, and no matter how good your drawing skills are, drawing a four-dimensional image is not really straightforward. So that's why we started with the 2D case, and why a lot of exercises and also in the exam will be probably in 2D, but of course 3D is the thing that we're mostly interested in graphics. And if we look at scaling, we see it's an obvious generalization, because if we want to scale it, we just have a third coordinate, we just have to add a third factor here, and since we only want to scale that factor, all the other values are set to 0. So this is a pretty straightforward generalization. The same is for the shearing. We already looked at shearing across the z-axis in relation to the homogeneous coordinates. I didn't really introduce it, but if you paid attention and you realize this is a shearing in 3D and not in 2D, so I already introduced it, but along the z-axis, because we moved everything from the xy plane to the z plane and then sheared in the z plane or along the z-axis in this plane for z equals 1. And of course you can also shear in other directions. So for example, if you shear in the x direction, then you take a matrix like this, because you see in the result you get then the x value increases or decreases depending on the y and z value and this factor d, and the z and the y value stay the same. And of course you can also do this in y direction, which I'm leaving out here. Good. So we see that if we move to 3D, then we need 4 cross 4 matrices, but what I said before for the points and the vectors stays the same. So they also get another dimension, which is a 1 for a location and a 0 for a vector. And so the most important thing is that, of course, when we move to 3D, not only that these are simple generalizations from the matrices, but the general framework that we introduced stays the same and works also in this higher dimension from 3D to 4D. Good. So yes, scaling and shearing are straightforward. Reflection and rotations are a little bit more difficult, also because of we are in another dimension now. We have in 3D now, not in 2D. We have to think about first, how do we do the reflection? For example, we could also make a reflection on a line, but generally in graphics we are more interested in reflection on planes, because these are just a situation that happen more often in graphics. But of course we could define it as a reflection on a plane in a similar way as we can do in 2D a reflection on a point or a reflection on a line. So we could do it with a line, but usually we're interested in planes. And rotation is usually done around a directed line. So you have a line or a vector that points in a certain direction and you rotate around that vector. Good. So yeah, let's look at the rotation first. What is the rotation, for example, for around the angle, a rotation of the angle theta around the z-axis? If we remember what we had rotation in 2D, for example, if we just look at the xy plane, then we get the rotation in 2D. And if you remember, that was the one that I have proven, a rotation around the origin, around the vector phi, counterclockwise, can be done with this rotation matrix. Now if we look at what happens to these points here when we do in 3D a rotation around the z-axis, for example this point here, if we rotate it here, we see that the z value doesn't change. The z value stays the same because it rotates around the z-axis, so it doesn't move in that direction. And the x and y values are exactly the same that we would get if we would rotate here in the plane. So the rotation matrix is cosine phi minus sine phi, sine phi, cosine phi, and here we just have 0, 0, 1, 0, 0. And that is our rotation matrix in 3D around the z-axis. Now be careful, these are not the homogeneous coordinates, because we're in 3D now. So if we have if we also want to do a translation, we have to add homogeneous coordinates, but then we will get a 4 cross 4 matrix. So this here, not these, but these are. Good. So we can rotate around the z-axis, but of course we want to do also different kind of rotations, for example rotation around a specific vector or a random vector. And not only a random vector that starts in the origin, but a random vector that is placed anywhere. So how can we do that? Again, we do this by combining different kinds of operations with each other. Doing this more complex operation by doing a sequence of more simple operations. So the idea is we have a vector and we have an object and we want to rotate this object around the vector. So what we do is first we rotate the vector to the z-axis, Then we do a rotation around the z-axis, and we just learned how to do that. That was pretty simple. And then we rotate everything back. So not only the vector, but also everything else. So we have to do a rotation of everything. So we basically have a coordinate system around that vector, and then we rotate that to the x, y, z coordinate system. Then we do a rotation there, and then we rotate everything back, and then we have our rotation. So what we need is these three rotation matrices. Rotation around the z-axis is simple, we already know that. Now, what are the other two rotation matrices? Let's start not with the first one, let's start with the second one. Let's assume we have rotated everything to the Cartesian coordinate system, then we've done the rotation, now we want to have it back. How would that matrix look like? Turns out that matrix is pretty simple, because if you think about what do you get, or remember, what do the column vectors of this rotation mean? And this is a rotation, it's just a linear transformation. So the column vectors are the images of the base vectors after the rotation. But if the rotation after the transformation, but if the transformation that we do is exactly the opposite, so the inverse rotation of the original one, so this was the original rotation, let's call it R, and that is then the inverse of it, we end up at our original vectors from the original coordinate system. So we just can write down, so if we call them U, V, and W, we just write, just write those vectors here, U, V, and W. So that is pretty simple. Now if we have that matrix, then the other one is of course also very simple, because it's just the inverse of it. So the inverse of an inverse is the original one. So we get here, by just building the inverse matrix, we get that. And if we use unit vectors, if we have an orthogonal matrix, if we use unit vectors with a right angle, then it's even simpler, because then we have a so-called orthogonal matrix, and an orthogonal matrix is a matrix where the column vectors are unit vectors that have a right angle to each other. And there is, we can prove that also in mathematics. Again, I will not do that, but just use it, this characteristic. If that is the case, then the inverse matrix of it is just the transposed. So we can just, we see here, this is just a vector U, this is just a vector V, and this is just a vector W. So we can basically just write this down. We just have to take this coordinate system and create our matrices from it automatically. Now, of course, there is one thing missing. I said we just have to take this coordinate system, but where does it come from? We don't have it. We just have a vector. We want to rotate around a vector, and then I said to do this we have to rotate everything, and to do the rotation we have to rotate a coordinate system, but we don't have it yet. And we need it to write down these matrices. So writing down the matrices is of course very simple if you have the coordinate system, but not if you don't have it. So what we need is basically we need to define ourselves a coordinate system where we have unit vectors with the right angle to each other. And then we can easily get these rotation matrices. And getting unit vectors is clear. We do that just by dividing it with the length. Then we have a vector of the length 1. If we have two vectors, getting a third one that is orthogonal to the first two is also pretty easy. We know that from if we do the cross product of two vectors, then we get a right angle to it, a vector with a right angle to them. The only question now is how do we get the second vector before we have the third one? And that can be done by a very simple trick. We just define any vector t which is not linearly dependent of the vector w, so not parallel to it. So we can, for example, just say t, we just take the lowest coordinate of w and set it to 1. Unless it is 1, then we set it to another value. And then we have a vector that is not parallel to the vector w. And then we can use that to create a vector that is orthogonal. So most likely t, since it was pretty much chosen randomly, is not orthogonal to w, but if we build the cross product with w, we get 1. So we get our first vector u, which has a right angle to both of them, including w. Now if we take the cross product of u and w, we get another vector, which then is our third one, and we can use it. And then we have our coordinate system, then we can easily get our rotation matrices, and then we can easily do our operation. Now, of course, this kind of approach or this kind of rotation is not unique, because the vector t was chosen randomly. It just doesn't have to be parallel to w. Other than that, we can choose, there's an infinite possibility to choose these vectors, but it doesn't have to be unique, because we only use it to do this first transformation, then we do the rotation and we translate it back. So if we do a rotation like this, let's call it R1, or we do a rotation like this, let's call it R2, and then we do, for example, a rotation 45 degrees, then we see this cube is then here and the 1 is here, and if we do a rotation 45 degrees here, we see the 1 is on this side and the 2 is on the other, and here the 2 is in the back. And if we then rotate it back with the correct rotation matrices, of course we will end up with the same one, because we put everything back where it was under that rotation, and everything here back where it was under that rotation. So it doesn't have to be unique, but as long as the rotation matrices are correct. Good. So another example is the reflection. Like I said, reflection let's also start with an easy case. What is the reflection for what is the matrix for reflection on the xy plane? Like I said, reflections in 3D are often done with respect to a plane. So if you think about, you have the xy plane. The first image is wrong. That's why I was confused. That was an old example. I forgot to remove that. Sorry for that. So we have the xy plane, and we want to do a reflection there. If you think about what happens to a point here, when we do the reflection on the xy plane, the x and y values pretty much exactly stay the same. Not pretty much, they stay exactly the same, but the z value just changes its sign. So the reflection matrix is, of course, once in the diagonal, and only the last diagonal has a -1, because that is the set value that changes then this the sign. And again, if you want to do a translation, you have to add homogeneous coordinates here as well. And this is what we need then when we want to do more complex operations. When we do we don't need it for a reflection or on a plane that is going through the origin, but we need it for a reflection for a plane that is anywhere else and not going through the origin. And how we do that, again, we can do this. I will not go through the details here, just explain the idea of it. And in the tutorials, then you will have an example. I think in the tutorial it's just an example in 2D, but the basic idea is the same. So we do this again as a combination of different operations. So first of all, we can move everything to the origin. Then we have exactly this plane here that goes through the origin. Then we do the reflection, and then we translate it back again. And this is why in this case we need the homogeneous coordinates. And the reflection in this situation here, remember what I said, what we learned, that we have here the homogeneous coordinates here, the zeros and the 1. Here we have the two values for the translation, which are the images of the origin under the affine transformation. So in that case, we have to here look at the origin here and where it will end up when we move it here. So this is basically this distance times 2, and then we have the set value, and the x and y value is still 0. So this will be our two values here. Now the question is, what do we have to write here? And these are the images of the base vector under the linear transformation. So not under this transformation, but under this one, where we have it do the reflection, which is a linear transformation. So we basically have to look at the three base vectors and then try to figure out what the image of that is, and depending on what kind of plane we have, we can solve this in a general way, or we can do it just by looking at this particular example. So for example, if you look at it in a 2D case, what we basically have is if this is in 2D, if this is our coordinate system B1 and B2, and this is our plane that goes through the origin, then we know that the reflection of this, have a right angle here, and then we want to have the vector B1 dash, which is then the reflection, and this is then here our B1 dash. So you just have to think about what do you have to do to get this vector, or how you calculate them in that case. So for example, one approach would be to use the normal vector from the line as a direction vector and this B1 as a support vector to create a line. So you have V1 and you have a line with a normal vector, and you can use that to create a line here. Then you can create that line to create the intersection point. Then you have the distance 1 here, and this distance here is, of course, if we call this D1, and this is also D1, and then you can specify where on this line this vector points to, the vector B2 points to. Yeah, this is, I hope you followed it, because otherwise you will have problems understanding my graphics here. Good, alright, yeah. So, any questions so far? No? Everything clear? Good. Then you should be ready for the next step. But first, since this is kind of a little break in the lectures, I usually like to make a stop here. And since the first part is a lot of mathematics and not really much graphics, I think it's also good sometimes to show a little bit of computer graphics. So the sound works. Does that work? Yeah. Good, yeah. So one of the reasons why I show this is, of course, because we already did a lot of stuff, but the other reason is also, of course, to remind you that you also have to pass an exam, and I hope you will do a little better. The exam is scheduled 24th, that's Tuesday in a week, 8:30. If you want to complain about that, feel free to do so, but not to me. I already complained to the administration last year when we had the same situation. I don't think it's okay, because last year we also had a situation that people had to stay with friends for the night because they were not able to come that early. I complained, but yeah, you see, they didn't really care much. So it is the general rule is if you come half an hour late, then you are still allowed to join, but you lose, of course, that time. So if you're coming from outside and you're arriving a little bit late, it's not that critical. That's also why in the first half hour no one is supposed to leave the exam, because as soon as someone left, of course, no one else can be allowed to join. Educar Gamma, that's what I have from the website. Make sure before you come that you check the official site again. Also, always check the website. If there is some last-minute announcement that I have to make, then I always put it on our website, the website of the course. For the exam, yeah, come in time, bring a pen, bring a student ID, and know the answers. That's basically what you have to do. There will be no books, notes, or electronic equipment be allowed. That includes cell phones because you can use your cell phones as a calculator. Also, I don't do it that you have to know the formulas, so you don't get a sheet. Of course, not the complex ones, but the standard stuff, cross product, sine and cosine, all the stuff that we used in the lecture. You should know that, but yeah, these are pretty simple things. I mean, cross product is not simple to remember, but it's not really that much. Good. Yeah, the exam will cover all lectures, including today, and the tutorials till the one that comes out next week. Yeah. Speaking of that, final comments on the schedule. Today's the deadline. Did anyone have problems with uploading, except for the one that I already know? If you had problems, contact me as soon as possible, which means after the lecture. I think the second assignment will be online tomorrow. I hope that we have it done by then if there are no complications. I meet with the teaching assistants later. That's why it doesn't make any sense to have a teaching assistant sitting there for 2 hours now after the lecture. So today there will be no one there. Next Tuesday, there is the introduction lecture from Maris about the shader programming, which will not be recorded. So if you want to attend that, which I highly recommend, then you should be there. But this is the introduction for the programming assignment, so it is not part of the exam. But since the programming assignment also counts for your grade, of course, it is highly recommended. Then next Thursday, there is no lecture. I always do this if it's possible to give you at least one date before the lecture to repeat the stuff, because I know, and I already said this at the very beginning, that I think the pure content of this course isn't really that difficult. It's more difficult that it is so much content that you need to know. And I often observe this in exams, that there is a simple question where you think, how can you possibly not understand that? And they just didn't solve the question. And I think it's not because they're too stupid, but just because they didn't have the time to learn it. Yeah, so this is why there is no lecture on Thursday. So you have time to prepare for the exam or start with the second assignment. And this is also why on Thursday we moved the teaching assistant, this one session on Thursday after the lecture, to the time of the lecture, because otherwise there is a 2-hour gap, which doesn't make sense. So you can come Thursday morning or in the afternoon between 1 and 3. And then on Tuesday we have the exam, and then afterwards there is lectures again and the regular schedule. Good. Are there any questions about lecture today or organization, exam? No? Then I hope to see you all on Tuesday for the practical lecture and the following week for the exam.